All right, welcome back, everybody. Today we're going to be doing section 6.4, which is all about trigonometric identities. This is the part of the course where we start learning a whole bunch of formulas and identities like the ones we'll see in this section. This is also usually the part of the course that people are like, oh no, this is why I really don't like trigonometry, because there's just so many of these formulas. The good news is I won't require you to memorize all of them. I will give you a sheet on the exams of the identities that you should not have to memorize, but there are some that you absolutely should memorize, and I'll be clear about which ones those are, and then I'll give you a list. In particular, there's about 6 or 7 that you really do need to have memorized if you want to do well in Calc 1 and Calc 2. But we'll get to that when we get to that. So let's get started. All right, 6.4. So here's an overview. We're going to talk about the definition of an identity first. We'll review some identities that we've already seen. Then we'll go through the process of how to establish or prove an identity with a whole bunch of different examples. And then you'll get to practice on the homework. So let's start with the definition. We say that two functions f and g are identically equal if and only if they are equal for every value of x for which both functions are defined. So in particular, we're saying that basically the function f is equal to the function g, and it doesn't matter what you plug into either function, you're going to get the same result. So if this condition is satisfied, then this is true for every x where they're both defined, then we call this relation, this equation right here, we call it an identity. An equation that's not an identity is called a conditional equation, and you've seen these for a very long time. I have some examples on the next slide. Sometimes when we want to emphasize that we're working with an identity, we will use this symbol, this little like triple equal sign, you could say. And sometimes because it doesn't even matter what the input x is, we'll just omit x entirely and just say that f is equivalent to g or f is identical to g. All right, so here are some examples. Example one are 3 examples of identities. So here's one. This is what you get when you quote unquote FOIL out x plus 1 times x plus 1. You'll get x squared plus 2x plus 1. It doesn't matter what number x is, this equation will be true for every single x that is actually every single x in the real numbers. So that's an identity. Same thing with this one over here, cosine squared x plus sine squared x equals 1. This is true for every real number x. It doesn't matter what x is, this will always be true, this equation. And then there's this one. This is actually how we defined cosecant. We defined cosecant as the reciprocal of sine. Well, you could also just establish it as an identity because it essentially is saying that no matter what x is, as long as it's in the domain of the cosecant function, it'll be true that cosecant of x is 1 over sine of x. So those are identities. Example 2 are some examples of conditional equations. So here's a conditional equation. 2x plus 5 equals 0. That's not true for every x value, right? This is the type of linear equation that you've had to solve many times in the past. In this case, this equation is only true when x is equal to negative 5 halves, right? So it does matter what x is. This equation is not true for all x's. And so that's why it's a conditional equation. It is not an identity. Same thing with this, right? Sine of x equals 0. That's not an identity because sine of x is not identically equal to 0. It is equal to 0 for some values of x, right? Some values, but not every value. And then same thing here, sine of x equals cosine of x. Again, this is not true for every x value because sine and cosine are not the same thing. So this is a conditional equation, and it only holds true for some values of x. And that's the difference between an identity and a conditional equation. All right, so yeah, like I'd mentioned at the very beginning of this video, in the next 3 sections and this section, we're going to learn many identities. Some you need to memorize, many of them you will not need to memorize. So don't feel pressured like we're going to get so many of these things. Just don't feel overwhelmed. Just remember that most of them you will have on the exam. You'll have a list. What I care more about is, can you actually work with the identities? Can you prove an identity in the appropriate way? That's what's most important. This is honestly one of those situations where if you did need to use one of these identities, most likely you're just going to be able to look it up anyway. unless you want to go into like competition level mathematics, like if you want to, if you want to compete or you want to take the Putnam exam, or if you want to do like an integration B or any of those like competitive mathematics competitions, then you need to memorize everything. But for most of us, you do not need to memorize all of these. Um, yeah, so some identities we actually already established, and we're going to recall them now. So there's the quotient identities. These are actually how we defined tangent and cotangent, so you should have those memorized already. The reciprocal identities, those are specifically how we defined cosecant, secant, and cotangent. Um, so you should have those memorized. The Pythagorean identity, cosine squared plus sine squared equals 1, this is one you definitely do need to have memorized. This one is not a definition like we used previously. This one is an identity, and you do need to know this one by heart. So memorize it if you have not already. There's also the quote-unquote tanning identities. That's what I call them. But the book just refers to all three of these on the screen as Pythagorean identities. I call them tanning identities because they're easier to remember when I remember the mnemonic I tan in a second, and then I cotan in a cosecond. So I call them the tanning identities. You can call them whatever you'd like. The book just calls all three of these the Pythagorean identities. All right, there's also the even and odd identities, which we talked about in a previous section. It's really just the even and odd properties of sine, cosine, tangent, and their reciprocals. Um, I think I have a note about this one. Yeah, a note about this one. I'll skip to this for a minute here. I actually don't recommend memorizing the even and odd identities. Instead, you should just try to remember the basic graphs of those 6 trigonometric functions and remember the symmetry properties of even and odd functions. So just a refresher, even functions are symmetric about the y-axis, and odd functions are symmetric about the origin. So if you can remember the basic graphs of sine, cosine, tangent, and their reciprocals, then you'll know what the even or odd, you'll know if it's even or odd just by looking at the picture in your mind. So that way you don't have to memorize this table of 6 identities. You don't really need to memorize it per se. And hopefully in the future, you'll work with them so much that it'll just be second nature. Well, you'll be like, oh yeah, sine's an odd function, so sine of negative theta is negative sine theta. But that takes time. um, the book refers to the identities 1 through 5 via the list that we just saw. It refers to these as the basic trigonometric identities. So just in general, I would say that you do need to memorize all of those, and you should also get comfortable with minor variations of those identities. So for example, the Pythagorean identity, you can rewrite like so: sine squared theta equals 1 minus cosine squared theta. So you want to be able to, you want to train your brain to recognize those types of patterns where you're like, oh, wait, if I see sine squared theta, I could replace it with 1 minus cosine squared theta. Or if you see 1 minus cosine squared theta, you realize you could replace it with sine squared theta. So you do want to get comfortable with that. And the next 3 sections will help you get comfortable with that. All right, so now how do we establish or prove an identity? So what does it mean? Establishing or proving an identity means using algebraic manipulations and previously known identities to show that a new identity holds. A new identity holds. So how do you do it? Well, you start with one side of a proposed identity and arrive at the other side through valid algebraic manipulations of the expression. And I'll emphasize this as we go along, because this is one of the biggest issues. You got to catch yourself so that you don't do this. If you want to prove an identity, you cannot start by writing the equality and manipulating both sides. So that's this cautionary note. If you start by writing the proposed identity and then you work on both sides, that's not a valid approach. And the truth is, you can prove anything if you do that. And it's because of this fact. So when you write down an equation like this, you're assuming that it's true, at least for some values of x, right? But if you're assuming that it's true when we're trying to prove an identity, you quite literally just assumed the thing that you're trying to prove. So that's not a proof, right? A proof is not saying, well, assume it's true, then it must be true. That doesn't make any sense. So it's very important that when you prove these identities, you start on one side and write your calculation as a chain of true equalities, and you will arrive at the other side, or arrive at the other side. So don't start with both sides and work on both sides. Start with one side and then get to the other side through algebraic manipulation. Which side do you start with? It turns out that you get to choose. Generally speaking, we will start with the side that has the more complicated expression. But let's talk about some other techniques that we're going to use. So there are 5 common techniques that we use to manipulate expressions and establish identities. The first 2 are what I always refer to as the most powerful techniques in mathematics. So a lot of powerful results really boil down to using these very simple methods, which is multiplying by 1 and adding 0. So whenever you have an algebraic expression, you can always multiply by 1 without changing the value of the expression. And if you have an algebraic expression, you can always add 0 without changing the value of the expression. So you haven't changed the value of it, you haven't changed the result, but you have changed the structure. So if you multiply by 1 in a clever way, you can change the structure of the expression so that you can manipulate it and massage it in just the right way to get something that's a new structure, but that is still equivalent in value. Same thing with 0, right? If you add 0, you're not changing anything, but if you add 0 in just the right way, then you'll be able to basically massage that expression into a new form that has a different structure, but the value of the expression is still the same as the one you started with. A good example of this one, we didn't do it in this class, is completing the square. Completing the square. So this technique is quite literally just adding 0. But you add 0 in just the right way, and then it lets you factor something, factor a part of an expression. All right, so that's my spiel for those. In fact, I'll give one little bit I'll add here. You can add 0, I'm sorry, you can prove the fundamental theorem of calculus by adding 0. So that's how powerful these 2 techniques are. The other techniques, rewrite the trig expression in terms of sine and cosine only. This is a good tip, especially if you've got tangents involved, tangents, cotangents. Write it in terms of sine and cosine, and if you're lucky, some nice cancellations will occur. You can also write sums and differences of fractions as a single fraction. This is something that you've done before in previous classes. You basically just, if you've got multiple fractions with different denominators, find a common denominator and write them as a single fraction, and sometimes that can help you reduce things and simplify things. And then there's always factoring. So number 5, factoring. If you want cancellations in fractions, you're always going to have to factor, get a common factor in the numerator and the denominator, and that will let you cancel. Okay, so enough of that. Let's do some examples. Let's just start with something basic. Let's just simplify the expression cotangent theta over cosecant theta. And, looks like, just realized that, well, okay, I won't be able to throw up the thinker and the speaker, sadly. I'll have to go through and adjust my settings here. But for now, oh yeah, that's right, because I adjusted the aspect ratio. So I can't throw up the thinker or the writing emoji or the speaking emoji, so I'm just gonna have to say it out loud. I apologize. But for now, think about how you would simplify this one for a minute and then try to do it on your own. All right, now let's take a look together. In this case, writing it in terms of sine and cosine is going to be the easiest way to do it. So here we go. We rewrite cotangent as cosine over sine. We rewrite cosecant as 1 over sine. Then we're dividing fractions, so you can flip and multiply. And what you'll get is you'll get a very nice cancellation right here. And so your final result is cosine theta. There you go. So cotangent theta over cosecant theta is actually just equal to cosine theta. All right, next, let's try this one. So now this is an actual identity. So what this equation is saying is that this side is equal to this side for every value theta. So we're trying to prove that this is true. Now, remember what you do is you start on one side and then you arrive at the other side. Do not start on both sides at the same time. So you can't just take this equation and basically tweak both edges until you get something obvious at the end. That is not a valid proof technique, because that proof technique involves you assuming that it's true to begin with, which is totally false, right? We're trying to prove that this is true. So start on one side and get to the other side. So maybe I'll say this real quick. You try. There you go. Since I don't have my emojis prepared, you try for a minute and then we'll do it together. All right, so let's try it together now. Um, I think I'm going to start on the left side. So what I'm going to do is I'm going to start with this expression and I'm going to manipulate it. And then I'm going to hopefully arrive at this side. And that will prove the identity. That'll establish that that the left side is equal to the right side. So here's how it goes. Oh yeah, so in this case, what I'm going to do is I'm going to multiply by a clever 1. I'm going to multiply this side right over here. I'm going to multiply this expression by 1 in just the right way that it'll make something nice happen. So here we go. What I'm going to multiply it by is 1 minus sine theta over itself. Okay, so first I want to just emphasize that this is equal to the number 1. So I have not changed the value of this expression at all by doing this. The value is still the same because any number times itself, any number times 1 is equal to that number still. So I've not changed the value, but I have changed the structure, and hopefully I've changed it in a helpful way. So here I go. Once I multiply by 1, I'm just going to distribute and multiply like I would normally. And there's something nice that happens. Check out the denominator here. When I do 1 plus sine theta times 1 minus sine theta, that's actually the structure of a difference of squares. So this is going to become 1 minus sine squared theta, right? So remember, difference of squares is this, a squared minus b squared equals a minus b times a plus b, like so. And that's what we have right here. Here's a plus b, here's a minus b. So when we multiply them, we get a squared minus b squared, which in our case is 1 minus sine squared theta. Now, what's cool here is 1 minus sine squared theta, that's just a tweaking of the Pythagorean identity. 1 minus sine squared theta is equal to cosine squared theta, just like that. It's equal to cosine squared theta. Now, we've got a factor of cosine theta in the numerator. We have 2 factors of cosine theta in the denominator, so we can cancel 1. And then we're left with 1 minus sine theta over cosine theta. And that's exactly what we were trying to prove, right? There you go. That's exactly what we were trying to prove. Yay! Okay, so before I go to the next example, there's a couple of notes and a couple things I want to point out about this example. So first, number 1 point I want to make is notice that I started on one side and I arrived at the other side. And the way that I did it was I used valid expression manipulations. That's why it's important to know the difference between an expression and an equation. All I really did was I took cosine theta over 1 plus sine theta. Let me get here. Yep, there we go. All I did was I took this and I multiplied it by 1. And then I massaged things in just the right way, got some cancellations, and then I arrived at this. So that's what you're going to do for every single one of these where you have to prove an identity. Start on one side and arrive at the other side. And all you can do is manipulate the expression. So notice here that if you look at the way that my work is written out, it's basically a chain of true equalities. And that's something I mentioned in a previous slide. Every single thing that you see on this screen is equal to everything else, right? So that's what's so amazing about this stuff. Let me see if I can emphasize this. This is equal to this right here. The value of those two expressions is the same, but this is also equal to this. The value of those two expressions is the same, and it's also equal to this, and it's also equal to this, and this is equal to, I mean, all these things are equal. This is equal to this. All these things are equal. There's a chain of equalities here, a chain of true equalities, and that's what you're trying to produce. A lot of times my students, when I'm in person, will ask, oh, do I need to write it that way, or can I just like do my own scratch work and give the final result? You need to write it this way. You need to practice writing it this way, because when you get to more complicated frankly, manipulations that you have to do, it's important that you organize your work in a clean, clear way. Because what you'll notice when you get into, Calc 2, like the first couple weeks of Calc 2, you're going to learn an integration technique. And if you are not aware that your calculations are written as a chain of true equalities, you're not going to be able to take the next step using that technique in Calc 2. So yes, do write it cleanly, clearly, as a chain of true equalities, starting on one side and arriving at the other side. All right, let's try another example. So once again, you try, oops, there's a U there. You try, and then we'll do it together in just a minute. All right, now let's try it together. One thing I'll say to start, generally speaking, you want to start on the side that has the more complicated expression. And the reason for that is there's more stuff for you to manipulate. So we're going to start on this side over here, and we're going to arrive at the other side, 2 sine of u. In fact, let me go back to my orange. Oops, erase. Go back to orange here. So I'm going to start on this side, and I'm going to just manipulate that expression in some way, and then hopefully, if things work out, I will arrive at the other side, 2 over sine u. So here we go. Surprise, surprise, the technique that I'm going to use here, once again, is multiplying by 1. So I'm going to multiply by 1 here and here. There we go. And when I multiply by 1 in this way, what happens is I end up with a common denominator for both of these terms, right? There are 2 terms here. Here's the first one. Here's the second one. I'm going to write them as a single fraction. That was the other technique in that list, right? I want to write them as a single fraction. How do I do it? I multiply by 1. I just got to multiply by 1 in the right way, which I did in this case. So I multiplied this expression by cosine over cosine, and this one by sine over sine. Now when I do that, I have something that's messier, but hopefully it will clean up. Hopefully it will clean up. Here we go. Now that these both have the same denominator, I can write both of these fractions as a single fraction with the same denominator. And so that's what's in the next line here. Okay. Now I just need to work with the numerator. So I'm going to distribute cosine, distribute sine. I'm going to get a big old mess up here. That's okay. It's okay if you get a big mess. Just take a deep breath. And then look at the pieces and see if there's anything nice that happens. Let's see. Anything nice? Oh, there is something nice that happens. Check this out. Look at this. Sine of u, cosine u, and negative sine of u, cosine u. Excuse me. Those cancel each other out. So those are out. And then now I'm left with cosine u plus cotangent u sine u in the numerator. No change in the denominator. But there's still more we have to do. Now, at this point, I'm looking at where I'm trying to end up. I'm trying to end up at 2 over sine u, right? Trying to end up right here. But there's some stuff that's in the way. There's a sine in the denominator already. That's nice. But there's a cosine there as well. So somehow I need to cancel a factor of cosine in the denominator. I've got one up here in the numerator, but in order to cancel, I would need a factor of cosine in here. And maybe you can kind of see what's going to happen next. What I'm going to do next is I'm going to rewrite cotangent u as cosine u over sine u. Right here. There we go. So now I'm using another one of those techniques, rewriting it in terms of sines and cosines. Now we get a cancellation. Sine of u cancels with sine of u. And now what we have in the numerator is we have cosine u plus cosine u, but that's 2 cosine u's. So that's how we're going to get that other factor of cosine u to appear in the numerator. We had cosine plus cosine, that's 2 cosines. So now we can cancel cosine, and lo and behold, we're left with 2 over sine u. Yay! All right, so this is essentially how the process goes. One thing I'll admit is that it's a very, very algebraic process. So if you enjoy algebra, then you're going to like these types of sections because it's honestly just a lot of expression manipulations. That's really what it is. Let's try another one. All right, let's prove the identity cosine theta minus sine theta equals this mess. Equals this mess. All right, and just like before, take a minute, think about it, say something out loud to yourself about how you think you would approach the problem, and then try it on your own. So I'll write it, you try, and then we'll do it together in just a minute. All right, let's try it together. General rule, we want to start on the side that has the more complicated expression, and I feel like this side is the one that's more complicated. There we go. So we're going to start with this side, and we're going to arrive at the other side here. And maybe just by looking at the structure of this expression, you can tell what we're going to use. We're almost certainly going to use even and odd properties of sine and cosine, right? Sine is an odd function, cosine is an even function. So we're going to be able to basically pull out those negatives from inside those functions to the outside, or just eliminate them entirely. So here we go. Starting on that side, here I'm going to just apply all of the even odd properties at once. Sine negative theta becomes negative sine theta, cosine negative theta just becomes cosine theta, and so on and so on. There we go. Now, there's something cute that happens here in the numerator. Take a look at this structure right here. Let me erase the other pieces here. Sine squared theta minus cosine squared theta. Now, that's not an identity, even though it might look close to one, but it's not an identity. However, it is a difference of squares. It's sine squared minus cosine squared, and we can factor that as sine minus cosine times sine plus cosine, which is exactly what we get here. Oops, exactly what we get right here. So now we've got sine theta minus cosine theta in the top. We've got sine theta plus cosine theta as in the top. Those are our two factors. In the denominator, both of those terms have a negative associated with it, so we can factor out the negative, and in the denominator we'll get this. Then something nice happens. We can cancel the sine theta plus cosine theta, and lo and behold, we are left with sine theta minus cosine theta. And there it is. Right? Not too bad. Just want to emphasize again that we started on one side and arrived at the other side. We did not start on both sides and get to something that's obviously true at the end. So just keep that in mind when you're doing these things. Okay, let's do one more example, and then I have some general notes, and then we'll call it a day. So just like before, you try to do this one on your own, think about it for a minute, say something out loud that you recognize, or maybe a technique that you would try just by looking at it, and then we'll do it together in just a moment. All right, let's try it together. So when I look at this, clearly I want to start on the left side because that's very complicated. That's much more complicated than one. Um, Incidentally, one of the reasons you want to start with the more complicated expression is because a lot of times if you start with the simpler one, it's really hard to tell what you should do first, right? It's almost like when you have more stuff to like move around and massage and play with, it's easier to get this result. But if you start with something very simple, you have to basically invent or create some some trick or some manipulation out of thin air that's going to get you to the harder one, which is difficult to do. So I'm going to start on the right or the left hand side here, and just looking at it, I see a lot of tangent, cotangent, sec. I see a lot of reciprocal functions. So I think what I'm going to do is I'm going to write everything in terms of sines and cosines first. Here we go. It'll be a little bit messy, but that's okay. Remember, just take a deep breath. Look at the little pieces. Don't try to do the whole thing in one step. Just try to do it step by step, piece by piece. And the cleaner and neater you write your calculations, the less stress you will feel. Uh, this is one of the reasons why you should practice writing these as chains of true equalities, because when your work is nicely organized, you can trace back any errors you might have made, and you can figure out how to proceed from there. So first thing I did was convert everything to sines and cosines. That's what I have here. Now, surprise, surprise, I'm going to use one of the most powerful techniques in math again. I'm going to multiply by 1. But in this case, I'm going to multiply by 1 in this form. There we go. Multiply by 1 in that form. And now the way this is going to work, this kind of depends on how you were taught this in the past. There's more than one way to manipulate an expression like this, but I like this method because when you distribute the cosine v sine v to both of these terms over here, it's going to cancel with something in the denominator of those two fractions. So when I distribute it to this piece here, the sine v over cosine v, the cosine v will cancel. And what I'll be left with is sine sine, which is sine squared. And when I distribute this cosine v sine v to this one, the sine v's will cancel, and I'll be left with cosine v times cosine v, which is cosine squared v. So that's what happens in the numerator. You're actually left with this, this in the numerator. But then what's also cool is when I do the denominator, let me highlight it here. When I take cosine v sine v here and I distribute it to this term, notice there's only one term in the denominator. It's 1 over cosine v times 1 over sine v. Well, if I multiply 1 over cosine v sine v by cosine v sine v, they cancel. They cancel, and so I'm just left with 1. So, voila, we have sine squared v plus cosine squared v, and that is the Pythagorean identity. So we can just jump right to the end. We can write it as 1, and we are done. We have now established the identity, started over here and arrived there. And that's how you do it. Yeah, so that's pretty much how you do it. A couple last minute notes here. I've already said them a few times. I know I've said them at least once. Generally preferable to start with the side containing the more complicated expression. Just use the 5 common techniques that we saw above. And then the process is primarily just algebra. So this is like the most algebraic part of the course, I would say. Although, I suppose when we get to some stuff involving the conic sections and polar coordinates and stuff, that's also pretty algebraic. But frankly, this is just a lot of algebra. All right, so that's it. Let's play. Now you should go try the homework out. And if you need to come back and review these examples, you can. You can always look at the slides. But other than that, let me get my little outro prepared here. I'll see you next time.